Welcome to Algebra 2, Semester 2, Unit 9, Section 9.6. This is one of the funnest sections, I think, of this entire unit, and it's because we're exploring conic sections. Now, if you happen to be one of my students that ends up doing projects and things, there's a lot that you can do with these. Your copy is not as clear as what's on the video, so you may want to enhance your copy. Since we don't have color copiers, I couldn't do a lot with that. Basically, I wanted to explain, and I've just got this Play-Doh. I did my best job of making 2 cones with this. It's not perfect, but you can kind of see it's just like here. It's a double nap cone. It comes in near the center. And we can actually slice it and see when a plane cuts straight through a cone. Let's just cut straight through this cone. If I had made it perfectly round, you could see we have a perfectly round circle. That's what we're graphing on a two-dimensional graph. When you see a circle is a slice with a plane cutting right through a cone. Now, let's put that back together the best that we can. Okay, now let's say instead of going straight through it, we went through it at an angle. Now we ask ourselves, well, what kind of shape would that make? As you can see, if we slice through it with an angle, we get an ellipse. Ellipse is this egg-type shape. So now let's put it back together. This poor cone. It's not looking real good. Okay, now we've got our double nap cone. It's coming in at the center. And now we're thinking, well, there's got to be a parabola shape, because all of these shapes, the circle, the ellipse, the parabola, and the hyperbola, are called conic sections or conics. And that's because they can be made with slices of a cone. Okay, so if we take this, now, instead of cutting through straight across to get the circle, or at an angle to get an ellipse, we actually angle it right down through the bottom of the cone and up on the side. We'll go a little bit deeper. And now you can see we have what we call, if it was a little bit better of a cone, we have what you call a parabola. It's shaped right there. Shaped right there. This should be flat. Sorry about that. So that's the parabola shape right there. Now what's interesting is if we continue that slice on down here, on this part, now with our flat ends, which aren't quite flat, you can see the hyperbola. It goes that way and it goes that way. So when we're graphing these, we're actually looking at a two-dimensional shape created by a three-dimensional object being sliced and laid on a two-dimensional plane. Okay? If you want to play with the Play-Doh and make any of these slices, I've got 2 tubs of Play-Doh over in my closet, and you can definitely have a little bit of Play-Doh time to mess around and look at those. They're kind of neat. And then you can see if there's any other shapes that you come up with as you just make a straight slice through those. So I'll have the little plastic knife and the Play-Doh in my closet. On this page, just enhance your drawings. You can see on the video, pause it. You can see on the video what it was supposed to be showing you. I'll darken this ellipse a little bit further. There's the circle, the parabola, hyperbola, which you graphed in Unit 10. And then up here it's showing how it slices right through, slices through at an angle, slices through the end, and through the side at an angle, and then slices through the ends and both sides on the hyperbola. Okay? So, the only other thing that I wanted you to know is that we call these conics or conic sections. That's just a general term for all four of them because they can be made with the double nap cone. So, I wanted to just kind of overview how we go through and we graph some of these just so that you can have an idea of how they're graphed in case it comes up. The first one we're going to look at parabola. You've already graphed the parabola. We are on page 8. You've already graphed the parabola in other formats. I just wanted you to be able to also graph it when it goes on the horizontal axis. You've seen it when it's vertical, seen it this way when it's vertical. I'm not so sure that you've seen the format of x squared equals 4py. Now that p is a point out here that's called the focus, but p is your foci, and the same distance back here behind it is called a directrix. Okay, so the cool thing about this is the same distance as this from the parabola. Okay, we aren't going to do a lot with these, just an overview. So the same thing happens when the parabola is going side to side, but in this case the equation is y squared equals 4px. Okay, that one you have not seen, so I wanted you aware of that one. You still have the p for your focus and your directrix being the same distance back here behind it. Okay, so you might see an equation sometime that indicates, okay, we've got to find the graph for this kind of a equation. When you see that, realize it's very similar form to the y squared equals 4px. So I just write the formula y squared equals 4px, and then I go ahead and I start to change this into that format. I put the negative 1/8 y squared right below the y squared and the x here. So I need to get the y squared by itself. In order to do that, I multiply this side by -8 and this side by -8. That'll cancel and I get y squared equals -8x. Well, -8 is setting in place of the 4p. So I know that 4p equals -8, divide each side by 4, and I know that p equals -2. So that tells me that the foci, which I had told you up here is p, okay, foci is always p. Well, that tells me that the foci is -2. Okay. Now, in addition to that, we can put in the directrix, which we know is the equidistance from that axis of symmetry. We know there's not a shifting going on. So that's our A of S. And we know that the directrix is 2 units the other way. With that much information, I would just like you, from this, knowing that it's the same format, just to give me a rough sketch of the parabola. Okay? Next one is a circle. When you see the format of an equation, x squared plus y squared equals a value, you can kind of look at that to see if it's a circle, because if you've got the x squared plus a y squared, then the number that they're equal to would be the radius. So here, x squared plus y squared equals 9. Well, 9 is 3 squared. So that tells me the radius is 3. Again, there's no shifting going on with the x or y. So I simply go to my origin and I go out 3 units, 3 units, 3 units, and 3 units. I do my best to draw that. I do have compasses in the room, so you can use those. Okay, another graph that we're going to look at is, okay, that was page 8. Now we move on to page 9. Another graph that we're going to look at is the ellipse. With the ellipse, you can spot it by the equations that I put down. You'll have x squared over a squared, y squared over b squared. They'll be added together. And then we want to set them equal to 1. That's the standard form of that equation. If it's horizontal, then this a value will be larger than the b value. Okay? If it's vertical, then the larger one, which is the a value, will be underneath the y instead of the x. So if the larger one is underneath the y, it's a vertical ellipse. If it's underneath the x, it's a horizontal. The vertices inside of the ellipse, there's 2. It would be like this, or like this. These are the foci still inside of there, but the vertices will be out here at the turning point on the circle. The vertices are on your major axis, so the horizontal would be here and the vertical would be up here. Okay? The co-vertices are out on the other perpendicular axis. That's the minor axis. Okay? So let's go down and just try a sample. Like I said, these are just a rough sketch, just to give you an idea of where we go with these and kind of have you comfortable when you see them to at least recognize what shape they are. Here we have 4x squared plus 25y squared equals 100. So we want to identify the vertices and whether or not it's horizontal or vertical. The first thing we need to do is put it in standard equation form. If you look up here, that was with equal to 1. So in order to make 100 equal to 1, we need to divide everything by 100. And now, when we reduce that, 4 goes into 100 25 times, so x squared over 25 plus 25 goes into 100 4 times, so y squared over 4 equals 100 over 100 is 1. Okay, so this shows us the value underneath the x is larger, so it's going to be a horizontal. And this is a squared, so the square root of 25 would be 5. That means that it would come out on the horizontal 5 units. That's going to be your longer axis. It also means that it could be the negative direction that I just drew. So it can be +5 or -5. On the y-axis, the square root of 4 is 2, so it could be a +2 or a -2. And then for our purposes, it's fine just to go ahead and sketch that ellipse in. I want you to make sure that you have in mind what the shape is so that when you get those critical points, you know what shape to fill in. Okay? The last one, the hyperbola. Again, this is just a rough sketching and just a rough idea of what these shapes are when you see them. We're just going to have a couple of them coming quiz. When we have the x squared, y squared with a minus between them, then that's going to end up being a hyperbola. And the easiest way I see just to sketch this, I don't get real critical on it. Later on we will discuss this real specifically, and then we'll have a lot more than just a general idea of how to graph it. Again, we put it in standard form. So we have 100, 100, and 100. We get the x squared over 25 minus y squared over 4 equals 1. Now, what happens on a hyperbola, remember it's going to be this shape and this shape. So what occurs is we still have that same kind of thing as what you had up here with the ellipse, where you've got the horizontal and the vertical distances from these numbers, but instead of it forming the ellipse, it curves outward. That's due to that minus, just how we saw transformations do things previously in other graphs, the same thing's occurring with that minus there. So if you just lightly sketch, I just kind of dash a line of a box in here off of those axes. And then what I do, trying to look for my ruler, there it is. What I do is I connect the corners of the box. These are called transverse axes, and they give you a great guideline here for a rough sketch of where the hyperbola is going. Okay, so there's our transverse axis. And now what I do is I realize that this point and this point are the vertices. And I just sketch that hyperbola about equally each direction, not touching those transverse axes. They're like asymptotes. It will not touch them, but it comes right out near them. Okay, so that gives you just a rough idea how to graph that. That's the end of that section of these notes. Thank you. Have a good day. We'll talk about this in class, maybe play with some Play-Doh.